While learning about ordinary differential equations, we got familiar with the Laplace transform, which we used to convert a calculus problem in the time domain into an algebra problem in the complex frequency or S domain. We can actually use Laplace transforms for pretty much the same thing to solve PDEs too, and if our solution u is a function of position x and time t, then taking the Laplace transform effectively gives us an ordinary differential equation in the multivariable function capital U of xs, where u is the Laplace transform with respect to t. We then solve that ordinary differential equation for u of xs, and then invert the transform to find our solution u of xt. This method is one in a class of methods called integral transform methods, and it's a common alternative to the separation of variables approach we learned in the previous tutorial. The thing is, the big annoyance in doing Laplace transforms is the part where we have to take the inverse Laplace transform, which we can only realistically do by trying to fit our function to one of the known results in the table of Laplace transforms. A workaround is to use a different transform called the Fourier transform. The Fourier transform of a function f is denoted f hat, and it's essentially a slice through the imaginary axis of the Laplace transform of f, as we can set our s variable to I omega to get our Fourier transform integrand. It's conventional to use the symbol omega when our function is of time t, while we use the symbol k when our function is of position x. These symbols represent frequencies of waves in time and space respectively. Omega is called the angular frequency, while k is called the wave number. The main advantage for using the Fourier transform to solve PDEs is that Fourier transforms can actually be inverted analytically using a formula that is almost identical to the Fourier transform itself, just with the sign on the exponential flipped and with a scale factor out front. This gives us a result called the duality property, allowing us to effectively use the Fourier transform table both ways. The convolution theorem also works for Fourier transforms. The Fourier transform of a convolution is the product of the individual transforms, and in the context of Fourier transforms, we will usually define the convolution as having infinite bounds. Unlike the Laplace transform, the convolution theorem for Fourier transforms works both ways, in both the time and frequency domains, thanks to the duality property. Let's shift gears for a moment to look at something called the Fourier series, which will initially seem unrelated to all this, but then will come back around and make the connection. Recall that we can represent any general continuous function f of x as a Maclaurin series, which is where we find coefficients a, n that should be multiplied by a sequence of powers of x to make up the function. We can refer to those powers of x as basis functions, where each function, 1, x, x squared, x cubed, and so forth, is linearly independent. Finding the coefficient of a Maclaurin series is therefore like finding how much of each basis function to add up to make the function. A Fourier series is quite similar, but instead of using powers of x as the basis functions, we use the trig functions sine and cosine of x with frequencies of integer multiples n of a fundamental frequency k. So our basis functions are cosine of kx, sine of kx, cosine of 2kx, sine of 2kx, and so forth, all the way to infinity. And we also include a lone constant to add on top. To find the Fourier series of a function f of x given k, we need to find the coefficients of these basis functions, an and bn, which is essentially asking how much of each frequency is present as sinusoids in this function, and how much has an even component, like cosine, versus an odd component, like sine. These multiples of the fundamental frequencies are called harmonics, in analogy with octaves and overtones in music theory, and finding the coefficients of each harmonic is quite straightforward. The coefficients of the cosine series, an, is proportional to the integral of our function f of x times cosine of nkx, where we integrate over the region of convergence, which we can now choose with the variable capital T, and then scale by 2 over t. And likewise for the sine series, bn. The constant d is just the mean value of f of x over our interval. An important property of Fourier series is that if our function is a periodic function with period t, then if we set our interval of integration to be that period t, our Fourier series will converge everywhere because Fourier series themselves are intrinsically periodic. We can also exploit complex numbers to compress our coefficient sequences into one, giving us the complex Fourier series, where the basis functions are the complex exponentials e to the inkx, noting that we are now summing over both positive and negative integers n, and the coefficients cn are easily related back to the real case. Also, if we return to our real series of sines and cosines and choose to ignore one of them, setting all the a_n's or all the b_n's to 0, then we get what's called a half-range series, which is a very useful simplification for when our function f of x is either odd or even, in which case we can express it in terms of either just sines or cosines, respectively. So in summary, Fourier series tell us how much of each frequency of sinusoids we can add together to make up any given function. So to find a Fourier series of a given function in general, we just need to choose an appropriate fundamental frequency k, spot any easy simplifications, and evaluate the integrals for the coefficients. For example, let's look at this square wave function, which is discontinuous but periodic with period 2. We can see that choosing a fundamental period of 2 will be a good choice for a Fourier series of this function, so k will be 2 pi over 2, which is pi. We also see that it is an odd function, so we can say that all cosine terms in our series must be 0, so we are really now finding a half-range Fourier sine series. It is also clear that the mean value over a period between the integers is 0, so the constant d will be 0. We can therefore go ahead and find the coefficients b sub n in the Fourier sine series of f of x by finding the integral of f of x times sine of n pi x across a period of 2 between the integers. Since the function is discontinuous at x equals 1 within our range, we must split the integral up into 2 parts. We will then evaluate the integrals and make use of the fact that the cosine of 2n pi is always 1. And the cosine of n pi alternates between -1 and 1 for integers n. And we get our Fourier series expression as shown. But dealing with discontinuities can sometimes be a little messy, so we will show an alternative method that is often faster when many such discontinuities are present. Let's go back to our graph of f of x and differentiate it with respect to x. The gradient is 0 everywhere except the integers, where we will get Dirac delta functions spiking up and down, where the function rises or falls by 2 units. The Fourier series of this derivative function will have only cosine terms, so we can write down the expression for a sub n as shown. But notice that since the function f prime of x only contains Dirac delta functions, it is very easy to integrate because we can just apply the sifting theorem by subbing in the values of x where the Dirac delta function spikes, 0 and 1, into the trig function, remembering the scale factor of 2. We therefore get the following as the Fourier series of the derivative of f. All that's left to do is integrate this series term by term to get the Fourier series of f of x. Cosine of n pi x becomes 1 over n pi times sine of n pi x, and the constant of integration corresponds to the mean value of f of x, which we already know is 0, so we get the same answer as before. It is very often the case that sketching out a given function f of t, as we have done here, will help us calculate Fourier series, allowing us to identify periodicity, odd and even functions, mean values from symmetry arguments, and more. When we evaluate the integrals for the Fourier coefficients, we can also often exploit orthogonality of the sine and cosine functions, where we can say that the integral over a period of the products of any 2 sines with different frequencies, or the product of any 2 cosines with different frequencies, will be 0. In the next tutorial, we will bring this Fourier series and the Fourier transform from the start of this tutorial together to uncover a beautiful hidden connection, so make sure you've got the basics of Fourier series and Fourier transforms covered before we get to the really interesting stuff.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.